Everyone, my name is Pratham Patel and today I am going to present a case study on designing a 4-bit binary counter using JK flip-flop. Counters are extremely important in digital electronics. They are used in clocks, timers, calculators and even microprocessors. In this presentation, we will explore how counter works, especially the role of JK flip-flop in building a reliable 4-bit binary counter. Let's begin with what a counter really is. A counter is a sequential circuit, meaning its output depends not just on present input but also the past state. It has memory. It works by counting clock pulses and representing the count in binary format. The counters can either increment or decrement with each pulse, and there are many types: asynchronous, synchronous, up counter, down counter, and up and down counter. These types serve different timing and control purposes on different systems. In a 4-bit binary counter, we are using 4 flip-flops, each representing 1 bit. The counter counts from 0000 to 1111, which is 0 to 15 in decimal. After reaching 1111, it resets back to 0000. Each bit in the binary number stands for a power of 2. So basically, a 4-bit counter can hold 2 raised to 4, which is 16 different values. This is the foundation of how digital electronics processes time, loops, and sequences. Now let's talk about JK flip-flop, which is the building block of our binary counter. It has two inputs called J and K, and it works with a clock signal. The special thing is when both J and K are set to 1, the output keeps flipping between 0 to 1 with every clock pulse. This flip in the output is what helps us count in binary. That's why JK flip-flop is very useful in digital counters. Truth table of JK flip-flop. This truth table explains how JK flip-flop behave. If J is equal to 0 and K is equal to 0, the output stays the same. If J is equal to 0 and K is equal to 1, it resets to 0. If J is equal to 1 and K is equal to 0, it sets to 1. And most importantly, if both are 1, the output toggles. This makes JK flip-flop more versatile than other types of SR flip-flop because they avoid undefined state. You can see the timing diagram of the JK flip-flop. It shows how the output changes when clock pulses are given. When both J and K are 1, the output starts flipping between 0 to 1, but this flipping happens only when clock signal goes down. This is called the falling edge. This edge-triggered behavior helps us control exactly when the output should change. That's how the counter moves from one state to the next at the right time. Counter circuit. They cascade 4 JK flip-flops, meaning the output of one is connected as the clock input to the next. Only the first flip-flop receives the external clock. This way, the flip-flop toggles one after the other, forming what's known as a reaper counter, which is a type of asynchronous counter. This table shows the exact output of the counter for each clock pulse. From pulse 0 to 15, the counter steps through all of 4-bit binary combinations from 0000 to 1111. On the 16th pulse, it reset back to 0000. The automatic rollover is what makes counters so useful in repetitive digital tasks such as looping sequences, digital clocks, and event tracing systems, where the same pattern needs to be repeated after a certain number of steps. Understanding this behavior is a key when designing timing circuits and control systems in the digital electronics. Counter works step by step. The first flip-flop changes its state with every clock pulse from 0 to 1 or 1 to 0. The second flip-flop changes only when the first one goes from 1 to 0. The third flip-flop changes when the second one goes from 1 to 0 and the fourth one does the same. Each one waits for the previous one to fall from 1 to 0. This creates a chain reaction. Because of this reaction, the flip-flop together counts in binary going from 0000 to 1111. This is how we get the counting behavior of any asynchronous counter. To make this counter work, first we set J and K to 1 in all flip-flops. This makes sure they toggle, which means they switch between 0 to 1 every time they got a clock signal. Next, we connect the external clock to the first flip-flop. Next, the output Q of each flip-flop is used as the clock input for the next one. This creates a ripple effect, which with each flip-flop triggers the next. This design is simple and easy to build, and if we want a bigger counter, we can just add more flip-flop to make an 8-bit or even 16-bit counter. JK flip-flops are great for building counters, and here's why. They toggle smoothly and reliably, which means the counter works properly without issues. They don't need any extra logic gates, so the design stays simple. We can use them for both up counting and down counting, which makes them flexible. And unlike SR flip-flops, they don't have any undefined states, so they are more stable and reliable. That's why JK flip-flops are best choice when designing binary counters. In digital electronics, we use counters to count numbers using clock signals. There are two main types, synchronous and asynchronous. In a synchronous counter, only the first flip-flop gets the clock signal and other follows one after another. This can cause small delays, so it's slower but simple to make. In synchronous counter, all flip-flop get the dog signal at the same time, so they all changes together. This makes it faster and more accurate, but but it needs a slightly more complex design. So in short, asynchronous is simple but slow, and synchronous is faster but a bit harder to build. Now let's compare two counter types. In a synchronous counter, the counter is applied only to the first flip-flop and the rest relies on the output chaining. In synchronous counter, the clock is given to all flip-flop at the same time. Synchronous counters are faster but more complex. Asynchronous counters are simple but have more delay due to ripple effect. Now basically, what is ripple effect? The propagation of a signal through a series of interconnected components causing a delay or a series of delays that can impact the all-over timing and performance of a circuit is called ripple effect. Binary counters are used in vast variety of real-world applications: frequency division in signal processing, digital timers and event counters in traffic lights and stopwatches, digital clocks to count seconds, minutes and hours, microprocessor to control loops and operations. Even microcontrollers like Arduino use binary counters in their core functionalities. One limitation of ripple or asynchronous counter is propagation delay. Each flip-flop needs to wait for previous one to toggle. As more flip-flops are added, this delay increase, which can affect timing accuracy. That's why synchronous counters are preferred in high-speed circuits. They avoid this ripple delay or yes, this ripple delay. To test and visualize how our counter works, we use digital simulation software like Proteus, Logism, and Multisim. These tools allow us to build the circuit virtually and apply clock pulses to the counter. We can then observe the output of each flip-flop in real time step by step. This helps us verify whether the counter is counting correctly from 0 to 15 and resetting after that. Simulation is very important part of digital electronics. It allows us to test the logic and find any error before we build the actual physical circuit. So instead of wasting time and components on mistake, we can fix problems early and make sure the design is working perfectly. That's why simulation is considered as a smart and essential step in modern electronics design. When designing digital counters, there are few key challenges we often face. One is power consumption. Every time a flip-flop toggles, it uses energy in large counters which many flip-flops. This can lead to high power usage, especially in systems when energy efficiency is important. Another challenge is propagation delay, especially in asynchronous counters. This each flip-flop wait for the previous one. The delay adds up and can slow down the entire circuit. Also, as we increase the number of bits, the design becomes more and more complex. More components meant more chances for errors and more time spent troubleshooting or debugging. To overcome these challenges, we use low-power flip-flop to save energy and switch to synchronous counter for better speed and accuracy. Synchronous designs make all flip-flop respond at the same time, reducing delays and improving overall performance of the circuit. This solution helps us build counters. They are both efficient and reliable even as the design grows in size. Now let's talk about the future. In future, the counters will become more efficient and integrated. Synchronous counter will dominate in this fast processing environment, and low power flip-flop will reduce energy usage, especially in IoT devices. And counters will be embedded into robotics, AI systems, smart applications for like better design and better performance. To conclude, a 4-bit binary counter using a JK flip-flop is a foundational concept in digital electronics. It teaches us about logic, timing, memory, and how we can create more complex systems from simple building blocks. Counters are everywhere, from computers to stopwatches, and the JK flip-flop ensures that they work smoothly and efficiently. And the last slide everybody is waiting for. Thank you for watching my presentation. I hope this helped you understand how a 4-bit binary counter works and the key role that JK flip-flop plays in digital design. Thank you. Have a great day.